Good morning. Welcome to NPTEL course Transfer Phenomena in Bioprocessing Week 4. So, last class we discussed about the net positive suction head and then how it's working. But this lecture, today lecture, we will discuss about the fluid flow measurement. So, how we can measure the flows, there is a flow is there and how we can measure. So, normally the controlling material, the flow is very crucial in chemical and processing plants. So many chemical plants are there and the processing plants are there. It's a very difficult to control the flow here. So many of these compounds are like fluids, the flow through the pipe, some other thing. So the fluid flow is measured using different type of devices. The simple method for measuring the fluid volume include gas and water meter as well as positive displacement pumps. So currently the current meters we use here, the spinning elements such as propellers or cups or different type of finally that we have to measure the velocity. That's very important. The velocity is here, the unit is meter per second. The velocity we have to measure. So what are the different type of the fluid flow measurement here? The different type of device we are using here. One is the pitot tube, that's a standard one. Then orifice meter, then flow nozzle meter, then finally the variable area flow meter. These are the devices to measure the flow measurement for, we will use always the chemical or industrial process. So other type of flow meters also there, it includes turbine, then thermal gas mass flow meters, some magnetic flow meters, so positive displacement flow meters, the like different type of the flow meters are there, other type of flow meter also we will use here. So now we will discuss the pitot tube. The pitot tube measure the local velocity at a given point in the flow stream by converting kinetic energy into dynamic pressure energy. So what is kinetic energy? We already discussed of mv square. We always write the kinetic energy. But the kinetic energy how we convert is here, the P by pressure energy, P by rho g. So basically the kinetic energy converting to pressure energy. So then it's a measurement taking place. So here the kinetic, the basic Bernoulli equations are there. There is a potential energy, but since the both are same, then the potential energy is 0. So only we are taking the kinetic energy, that's of mE square, then the dynamic pressure energy. There is a dynamic pressure energy at a stagnation point. So this is a pitot tube. One is the first one is a simple tube, another one is a tube with the static pressure holes. So there is the 2 point is there, one is the point 1 that is called a static port, it measures the undisturbed fluid static pressure, that is called P1 static pressure. So if you measure what is this point, that is called P1, then what is the velocity? Velocity is a V1. So we call it as a velocity because of point 1, then the static pressure is P1, then velocity is a V1. Same way for point 2 that we called as the impact port, it is positioned the same place, the perpendicular flow to capture the stagnation pressure, that is a P2. So where is the P2 here? P2, but the P2 the velocity is a V2 is a 0. Why V2 0? Always the tip velocity V2 equal to 0. So if somebody asks what is the dynamic pressure head? The dynamic pressure head is the difference between impact and static pressure. The P2 impact pressure P2 that we called as the impact P2, then P1 is the static. So the difference between the P2 minus P1 that corresponding to the kinetic energy of steam. So the P2 pressure energy, because the first point still we discussed the relation between, we are going to discuss here kinetic energy and the pressure energy. That's the relation here, and here the static pressure. What the difference between impact pressure is P2, then the P1 is the static pressure. So this is the problem, the figure given here, On second repeat, but the pitot tube is give for normally converting kinetic energy to pressure energy. There is a two port is there, one is a static port, then other one is for impact port. Then always develop the pressure and velocity. There is a pressure P1, velocity V1, the for point 2 there is a velocity V2 0, then the pressure is P2. The pressure difference is the P2 minus P1. So, this is a very famous Bernoulli equation. Normally we use, right, first is the pressure energy P1 by rho g at point 1, because there is a 2 points, one is point 1, then another is a point 2, the location 1 and location 2. So, P1 by rho g, then V1 square by 2 me square, then another is the potential energy. We always write a mg z1. Same here at point 2 we can write P2 by rho g, then velocity is a pressure energy, the velocity is a V2 square by mv2 square by 2, then potential energy mg is a 2. But the both 1 and 2 is a horizontal, that is z1 and z2 horizontal, automatically this will get cancelled. So, finally, we get only for pressure energy and kinetic energy at point 1, then pressure energy and kinetic energy point 2. So, then the simple modification, because we assume as a velocity V2 0, if you assume like here the velocity at a point wall always a V is a 0. Wherever V 0, then the shear stress is the tau max. So, the center point velocity is a V max, we call it as a maximum velocity, and that place this is a tau equal to 0. Wherever velocity is maximum, then the shear stress is 0. Wherever velocity is 0, the shear stress will become as a maximum. So, here the velocity V2 0, then after solving this, we will get a V1 equal to function of the pressure difference, then density, then Cp. The Cp is a pitot tube coefficient. We call it as a pitot tube coefficient. These are also dimensionless numbers. So, sometimes we will see drag coefficient. These all dimensionless number, dimensionless coefficient. So, this called as a Cp is a pitot tube coefficient. It is a dimensionless. So, what is the value? The value normally stands 0.982 to 1. So, they can fix based on the what type of they are using here. So, normally the Cp values start from 0.98 to 1. So, the problem 1 we will discuss. So, the pitot tube here used to measure the air flow, because that flow is the circular, the 600 millimeter diameter, the diameter is a 600 millimeter, problem already given. The pitot tube is placed in the center of that one, then there is a delta H is there, delta H is of 10.7 millimeter, the manometer reading 10.7 millimeter, they are converting in terms of everything SI units. Then the pitot tube coefficient, the Cp values 0.98, then there is a, this called a viscosity, we call it as a dynamic viscosity, is a viscosity mu is this one, then this point is a density, density is a 1043, density of air is a 1.043 kg per meter cube. So, density of water we know, all values we know, and of course, we know the formulas, just we have to substitute there, but they are asking calculate the velocity at the center and average velocity. What is this one? Then next question they are asking calculate the volumetric flow rate, the flowing air they are asking. Okay. First is they are asking velocity, then next is the volumetric flow rate. So, this is famous for Reynolds number, it is a NRE. So, versus is a figure given here. The graph we can take from here, that is NRE, Reynolds number, and the y axis is the average velocity by B maximum. So, from graph, if we know what is Reynolds number, we can get what is the velocity of the ratio. So, we take some 0.7 some values or 0.8 whatever value. So, from there we can calculate average velocity or sometime maximum velocity whatever from here. So, we know that the delta P equal to rho g h, we always write P equal to rho g h, because we start from P equal to F by A. F we can write MA acceleration of A. This M we can again write for rho G, rho the G is there, rho H, then A by A, then here another is come G. So, it will get cancelled, A will get cancelled, then it will go as a rho G. The P equal to, from there only we are deriving that one. So, P always we write a rho GH. Since the density is different, then we are writing rho W minus rho A. The density is different, then we are writing here. So, rest everything same values. G is a 9.8, then the H is the, what is the height of that one. So, we got a delta pressure. So, this equation we know already from U velocity. From this one, Cp is the pitot tube coefficient, and then pressure drop. You just substitute the value, then we get the value of U max. So, we know U max, that is the maximum velocity. Once then we know Reynolds number we called as a dV rho by mu. The V stands here inertial force and the mu is the viscous force. Normally, the Reynolds number is the ratio of inertia force by viscous force. So, all values are already given, you just substitute and get the value of Reynolds number. So, once the Reynolds number is this one, we know already the graph. From the graph, we will get the what is the value of average velocity by maximum velocity. So, from graph we got V bar is the average velocity by maximum velocity, then 0.85. So, then V bar we know V bar equal to the 0.85, the average velocity, the 13.9 is the V max, already V maximum velocity. So, we got average velocity. Then volumetric flow rate unit is the meter cube per second. So, now we know meter per second, if you multiply with the meter square area, then we will get the volumetric flow rate of this one. So, first we have to get A, then substitute A and then velocity already is there, we get the volumetric flow rate of this one. Okay. So, the first problem over, now we will move to second problem. The second problem saying the pitot tube installed along the axis of horizontal pipe 76 millimeter inner diameter. So, the temperature 40 degree, the pressure is there, the pressure is absolute pressure 10 by kilopascal, it convert in terms of Pascal. So, temperature of air also in terms of Kelvin. Then they are given here, calculate the rate of the flow of air, again they are asking rate of flow air. The reading of the differential manometer, the tube is 12 millimeter, that is a differential manometer reading here. Then the viscosity is here, these values. Then V average by V max equal to 0.81. Already they given the, because we no need to go graph. So, if you get the district for Reynolds number, then the average we can, already the problem itself the given value. What is the V average by V maximum? So, that we can use directly that one. So, then gas constant, the density of water, all values already given. So, whenever gas if you use, because there is a PV equal to nRT, so then this is P by RT equal to rho, we can write rho equal to P by RT. So, the pressure here, this is 1.105, already problem it was given, then R is the gas constant. So, we can write 8.314 based on unit, we can always change that one, the temperature. From there we can get the value of density of air. So, once the density of air done, then the pressure difference, that is the pressure difference, then always we write P equal to rho of GH, because rho GH. So, the rho is here and then the G value, H value, because the density of water we know, then air we know, then from here we can get the value of pressure drop. So, once the pressure drop done, so we know what is the equation, this equation already available, we can use pressure drop we know, density we know, then the Venturi, I think the coefficient they assume as a 1. So, from there we get a V max. So, once V max, the problem itself already they given like V average by V max equal to 0.81. So, from here we can get the average velocity. Once average velocity done, then we can go to volumetric flow rate, that is the default that one. For volumetric flow rate, we need area. First, then we have to find the area. Once area done, then from here we can get the volumetric flow rate of that one. Okay. So, we first discussed the pitot tube, now the Venturi meter. Venturi meter also to measure the volumetric flow rate, the fluids within a pipe, the pipe here. So, there is a two section, one is see the flow going as it is, that is called a main pipe. So, it goes to converging section, that is called converging section. Converging section, what happened? It's channeled into a smaller cross section area, the area is getting decrease. Though then here it's oscillate and decrease the static pressure. So, this point converging. Then next is a throat, the throat diameter, this one, that's called, we call it D2 throat here. Then other point is a diverging section. So, again whatever the main pipe same diameter, here also same diameter, and it's connected with the U-tube manometer, and we take this a reference, and there is a Z1 and Z2, that's a difference between this one, because the flow is horizontal, then always the Z1 Z2 same, then default the potentially what will happen, automatically get the 0. So, first section is a converging section, what we discuss here, converging section, how the converging section works here. It starts with a regular pipe, then suddenly the area get decrease, cross-sectional area get decrease. Then the throat diameter, that is a throat, this point, what we are discussing here, throat, it's a remain same, but only here where velocity reaches a peak, we get a velocity maximum here, but the pressure drop, there is a pressure difference is a minimum, pressure difference is a minimum, but the velocity is a, it reaches a very high peak. So, after this one, then again diverging section here, that is point diverging section, the pipe gradually widens, then it is a back to the original diameter, what are the original diameter, that one. So, there is a restoring the whatever the lost pressure, that will be a restoring here. So, again as it is, the pipe, the diameter is same here, whatever pipe we are using. Okay, it starts with the converging, then diverging, then in between the throat, here there we connected this all, U-tube manometer everything. So, the simple Bernoulli equation, we know that one, there is a, here there is a potential energy mg of Z1, then mg of Z2, because there is a 2 point, when you use the Bernoulli equation, there is a 1 and 2, 1 and 2, here the H1 equal to H2. That is meaning that the potential energy of Z1 or Z2 or H1 H2 both are same, then we will get a horizontal flow, it get automatically 0. So, then we know the continuity equation rho V A. So, density velocity A. So, since the both density is same, rho 1 rho 2 same, then automatically get cancel, then we can write only V1 A1 V2 A2. So, V1 stands velocity, then A1 here pi d1 square, V2 A2 pi dt square, the cross sectional area of that one. So, here we define as a beta equal to d2 by d1, that is a diameter ratio, the diameter of d2 by d1 we call as the beta diameter ratio. So, find to theoretical velocity, throat velocity V2 equal to Cv of, because this is a, after solving this one is substitute here, then after modification the beta here, then the Cv is a Venturi coefficient, we call it as a Venturi coefficient, then this is a 2 beta minus this one. So, we can even bring it inside also this one, since it is the inside root, we can bring it here. So, now see the problems here. So, this Venturi meter having the throat diameter 50 millimeter, the Venturi meter, the throat diameter is a 50 millimeter installed in a pipeline. Then there is internal diameter is a 120 millimeter, internal diameter is a 120 millimeter, that is a 0.120 meter. It used to measure the flow rate of water with a density, what is the density here? 998 density here. Then there is a pressure drop across the Venturi meter 120 kilopascal, and again converted into some pascal. There is a Venturi coefficient, Cv value is also there, this is called as a 0.97. So, they are asking calculate the volumetric flow rate of water, that is not their Q value, Q you have to find it. So, the volumetric flow rate here through Venturi meter, the Q equal to CVA2, then do delta P, that is a pressure drop, and then rho, the beta is the diameter ratio. So, the beta we called as a d2 by d1. So, the area cross section area by d2 square by 4. So, we know the value, what is the diameter ratio, this is 50 by this one. So, we will get the beta value here, this value you substitute, then we will get the 1 minus of beta power 4 value. So, there is a throat area also we can get it, and throat area also done here. Then the velocity term, the 2 value we know, then the pressure drop already the problem itself given, then the density also there, density of this one, then we can get the what is the velocity. So, once the velocity done, then we have to calculate the flow rate. Flow rate equal to velocity into area. The velocity, what is velocity? Velocity is meter per second, then area is the meter square. So, from here we will get a volumetric flow rate. The volumetric flow rate is a meter cube per second. So, the problem 3 over, then problem 4 the same way, but here we are using the hexane. The density is a 0.60 gram per centimeter cube. You can convert 660 kg per meter cube to solve in SI units. So, flow through the cross-sectional area A1, the velocity is already given. At some point of downstream, the venturimeter, the throat cross-sectional area, that is a A2. Then the diameter of the pipe and throat, the pipe diameter is this one, and throat diameter is a 9 centimeter. Then manometer containing specific gravity, 6 they are using mercury. I think this then is called 13.6 specific gravity, because mercury is here, the specific gravity normally 13.6. So, we can write 13600 kg per meter cube, the density of mercury. So, it is connected between upstream and throat tape. Then the venturi discharge coefficient CV equal to 0.97. So, here they are asking what is the pressure drop delta P in kilopascal, then they are asking what is the corresponding difference delta H value in mercury registered by the manometer. The same problem. So, here this is the first one we called A1 area 1, and this one the throat A2, the difference is delta H. The whatever velocity we are following, the same velocity here. So, here beta equal to d2 by t1, that is the ratio of diameter this one. So, it is called a diameter ratio. So, once we done 1 minus beta power 4, of course, we have to use the continuity equation. Continuity equation what is one? Again rho 1, rho 2. So, density is constant, we are cancelling. So, we know A1 is a pi by 4 d1 square cross sectional area, same way for A2. So, after this solving, then we get the value of V2, velocity of throat velocity 11.2 meter per second. So, once this is done, then we know the pressure drop we can calculate. There is a Venturi coefficient, the problem itself already given 0.97 Venturi coefficient. So, the densities are here, then velocity. So, from here we can get the value of pressure drop, that is a pressure drop. So, for the pressure drop is here 41.2 kilopascal. So, this one next the pressure drop here, we want to get the head of that one. So, here we can always use the P equal to rho g h, the pressure equal to the product of density, then gravitational, then h is the elevation. So, rho g h here. So, since the density is different, because density of two different density we used here. So, then we are using different density here. The density of mercury we know 13.6 of this one, then the density of hexane, the problem I think we discussed the hexane. The hexane density also there. There are two type of fluids, one is the mercury, other one is the hexane. So, there is a difference between mercury and this one, then we will get from here delta H, that is the head of that one, 0.325 meter. So, this is the last problem. So, here the Venturi meter same way with endents of diameter 0.25 meter, that is the inlet diameter is a 0.25 meter, because normally inlet diameter will come, then the throat is again will go very always lesser than the values, because the D2 throat diameter always will be a less compared to inlet diameter. So, this is the throat diameter 0.15 meter, then the coefficient of discharge, the CD value is the 0.98. Then the specific weight of gas is there, we write as a gamma A, it is there already, the discharge coefficient 0.98 here, we are 0.98. Then the specific weight of gases 24.53, 24.53. Then there is a manometer reading as other 0.08 meter of water. Then specific heat of water also here 9810 Newton per meter cube. So these all already given here. Now we have to calculate what they are asking here. Calculate the volumetric flow rate. Calculate the volumetric flow rate. So the velocity at the throat, the V2 equal to the CV by this is already the famous equation for we will use for Venturi meter. The CV is the Venturi coefficient, the problem is already given, then this is a diameter ratio, then there is a pressure drop P1 minus P2, that is a density. So first get the value of the density of that one. So the density of gas we got the value of 2.50 kg per meter cube. So the pressure difference, there is a pressure difference P equal to rho, we always write rho GH. So then we know the gamma W gamma gas we got from here, the pressure drop value is the 782.84 Newton per meter square. So once the pressure drop done, then of course area here, the area is the pi dt square by 4. Then A2 here, there is a volumetric flow rate, the area already given, and then there is a velocity. So then from here we can get the what is the volumetric flow rate of this one 0.46 by meter cube per second. So then we know the diameter ratio, because the d2 by d1 the ratio we have to get that one. So once the beta for 4 done, then we have to get the throat velocity. It's already formulas available, the throat velocity. This is 1 minus beta power 4 and this is a pressure drop. From there we can get the V2 velocity. The V2 is a 26.29 meter per second. So once this done, then we have to finally actual discharge we have to get it. That's a Q equal to the CD is a 0.98, that coefficient. Then the what is the Q theoretical value from this one. The finally we can get it the volumetric flow rate of this one, actual discharge volumetric flow rate. So we got it from this problem. Thank you.